in our webinar series, and this one is about something called feature engineering. So this is a webinar that's especially relevant for people who are getting started in data science, thinking about getting a little bit more serious. Read the abstract. In many ways, feature engineering is the most important part of a data scientist's job. So as good as the data that you put into the model. So this webinar is going to be a quick introduction to what Python and some of the principles of feature engineering, and there's a lot more information on our website and on the internet that you can take a look at if you're interested in learning more. So just before we get started, the whole point of feature engineering is this idea of garbage in, garbage out. And I'll probably keep referring to that throughout the webinar, but the point is, if you don't spend time making sure your data is clean, and you've removed outliers, you've removed missing data, things like that, then no matter how good your modeling skills are, no matter how sophisticated your model is, it's going to impact your results that you get out. So more than half of your time, unless you've got a team of people working on you curating a data set, is probably going to be spent making sure your data is in the right format. World scenario where you're working in a company, or maybe you're doing research of some sort, and you receive data from somebody else, you can't just trust that it's going to be perfect. So a quick overview of what the webinar is going to cover. What I'm assuming here is that you have some basic knowledge of Python, but you really don't have to know much. If you're already a professional data scientist, a lot of this will be a review to you. So feel free to skip through, although you might learn some tricks or things that you didn't know. But this is kind of geared towards people who are just getting started. So we'll learn how to load in data from an external file, and I'll talk about in a minute the file that we're going to use. And we're using 3 packages today. The first one is called pandas, and you express data in Python kind of like an Excel table. So we call it a data frame, but it has rows and columns that we're used to working with. And we'll go through a few different things we can do with pandas, looking at the size of the data that we've put in, getting a look at what the data looks like, slicing out rows and columns, and finding and replacing missing values if they're there. The package is called Seaborn. It's a really visually appealing plotting package. So I'll show you actually 3 examples: a boxplot, a scatter plot, or a dot plot, and then the last one will be a heat map. Great, you can go on their website and check out. They have a bunch of tutorials and different examples of different plots you can do. So it's a great way, if you already have data, to kind of generate some inspiration on what you'd like to do. And then the last one will be a quick intro to scikit-learn. So at Cambridge Spark, we spend a lot of time with this package because it's the best machine learning and data science package. But we're just going to use a single function from it today to rescale our data. But if you can look up some of the free tutorials, or if you decide to join the conference or the 6-month data science course, then you'll get to use a lot more methods from this scikit-learn package. So I just want to cover this at the beginning in case people need to duck out early. We have some really great free tutorials on the website, so you can go to cambridgespark.com/content. One that's particularly relevant maybe when you finish this webinar is you can check out one. So this is just a little bit more about using pandas to slice data frames, get a look at your data, and that sort of thing. In less than 2 weeks' time, we have a conference coming up in London. So it's a 3-day conference. The first day is going to be talks from all sorts of different fields within machine learning and computer science. I come from a computational biology background, so I'm giving a talk about genome sequencing data, but there's all sorts of good stuff. And then the second 2 days are training, so you'll learn a lot more interesting techniques than the one covered today. So check that out. And then finally, if you're thinking about getting really serious, you can look into the 6-month applied data science degree. So it's actually every other weekend, over 10 different weekends. So it covers about 6 months, but it's only on the weekend. So it's something you can do while you're working, if you're thinking about retraining to be a data scientist or that sort of thing. So there's already a course going on now. and there's another one that's going to restart in 2018. So there's still a few spots left on there if you're interested. Okay, for everybody who wants to either try to run this alongside me, or if you're watching this later, this is all you should need. It's Python 2.7, and then you don't even really need the Jupyter Notebook, but it helps to visualize what we're working on. So you'll need to install pandas, scikit-learn, and the last one being Seaborn. I didn't put that one on there, but just run pip install Seaborn. Okay, so the data set we're going to work with today is from a website that I'll show you in a moment that has all sorts of useful machine learning data sets. And this one has a bunch of data geared around trying to predict heart attacks. So it's things like cholesterol level, blood pressure, measurements from an ECG, 13 different attributes that we're not going to go into the prediction side of this data set today. We're just going to take a look at the data, but this is something where you could try to build a classifier to predict whether someone's going to have a heart attack based on this data. So I'm just going to switch over to my notebook here. So this is a Jupyter Notebook. If you've never used it before, it allows you to create cells. We can put code in here. 2 + 2 is 4. You can print hello. And we can also change this to have free text. So this is something that if you haven't used before, you should really check it out. Okay, so the first thing that we're going to do is load libraries. These are the two that we'll need at the moment. The first one is called NumPy, and I'm just giving it a nickname here, that's MP. And the second one is called Pandas. This is the one that we're going to focus on. So you can see there's a little star that shows up there while it's running, and it doesn't print anything out, so that means it was successful. Okay, this data set we're using, if you want to visit this website and check it out, there's a little more information about it. It's called the Heart Disease Data Set. There's a little bit more information here. I've downloaded it and put it in the same folder as my Jupyter Notebook. So we can use this function read CSV because it's expecting the file. And if this dot just means it's in the present. If I hit the tab button, you can see all the files that are in there, and that's the data that we want to see. This is from Cleveland. There's a few other locations that they've taken this data from, but I just picked one. I already looked at the data ahead of time, and I see it doesn't have a header, so I'm just adding this extra flag here, and we're going to call it, what should we call it? Heart. So you're going to see the little star again, and it works. First thing that you generally want to do when you've loaded a new data set is you want to figure out how big it is, and you want to take a look at it and see what the data looks like. So this data frame heart has a number of functions that are attached to it, basically. So since it's a data frame, we can do all sorts of fun stuff to it. But the first thing that we want to do is ask, what is its shape? So you can see here it spits out this tuple, it's called in Python, and what you think it is. It has 303 rows and 14 columns. So the second thing we can do is say heart.head. What this does is just prints out the first 5 rows of that data frame we just loaded in. So you can see here, we don't really know what the columns are. It's given us row names, so we can maybe take a guess looking at some of these things. So this one, 63, 67, it's probably age. This one, a bunch of zeros and ones, not really sure. But you get the idea. A lot of times you'll receive a data set and you don't really know what the columns are. In some cases it might not matter, but we have this information luckily from the repository here, so it tells us what are all of the columns that we've used. So I'm just going to add these columns on. So the heart data frame has this attribute called columns, and we can just fill in the appropriate columns based on what it said on the previous page. So So that's probably blood pressure. This one's cholesterol. I don't know what FBS is. Best ECG. Black. Don't know what that is. You get the idea. So we've got all these things that would probably mean something to a cardiologist, but you know, for us as the data scientists, it doesn't necessarily matter in some cases what the features are. We can still learn something useful from them. Although one thing that you'll find if you spend a lot of time as a data scientist is that having some kind of domain expertise is really useful. Okay, so I've added the names of the columns here, and I can just show you again. If we look at the first few rows, there we go. Now it looks a little bit more reasonable. This is the age, this is the sex of the individual, etc. And that last column, num, a code that describes what stage of a heart attack they've had. So 0 is they haven't had one, and then there's 1, 2, 3, and 4, which are different grades of heart attack. So as you can kind of see from this data frame here, it's a format we're used to looking at. And there's a lot of simple things we can do to it. So this function iloc allows us to slice out certain rows and columns. So let's say I wanted the first, in case you didn't know, Python numbering starts at 0. So just to give you an example, this says give me rows 0 through 9 and all the columns. And we can see what it looks like here. You can say give me only the third row and give me columns 0 through 3. So in Python, you also, when I wrote 4 here, it doesn't include the fourth one. See here, it's taken this row, instead of printing it like that, it's printed it vertically. So age, sex, CP. If I made this back in this kind of tabular format. So that's one way you can access the rows and columns of this data frame. We call that slicing. Another way is, since we've named the access it by the name of the column, so we can do open brackets and age, for instance. And this is going to print out all of the ages in the data frame. But luckily, Jupyter is very helpful for us and puts this ... in the middle, so it doesn't print everything out. So you can see here all sorts of different ages. Maybe there's some relationship between age and heart attack. We'll get into that later. So the do is actually take out this last row. We called it num here. So the reason we do this is generally when you're trying to build a machine learning classifier, you're yourself ahead of time whether they have a heart attack or not. It's something that you want the computer to learn. So we're going to separate out these things that we call the attributes. A lot of times you'll see it called capital X, and we'll separate those from the target, as it's often called, which is the last row, which tells us what it is. So I'm going to use the same iloc that I did before. The colon means we're taking all of the rows, and we're going to take everything but the last column. So this is a kind of funny Python way of doing it, but the -1 here means the last column. And so this is saying from the first to the last column, but when we number things in Python, we don't actually take the last number. So you can see here, if we take a look at attributes, we can use head. Again, what does it look like? It's basically the same one as before, except we've dropped that last column. And we're not really going to use this one today, but let's just take out the last column of the original data frame, which is num. We can take a look at that one as well. It's probably going to print in that funny way like before, yeah. But as you can see, it's just the last column here, 2, 1. And if you're interested, you can take a look at that and see exactly how many types of outcome we have. So we can do num value counts. This is, again, another helpful function that pandas gives us. So taken this column of all the different outcomes and tallied them up for us. So there's 164 people in the data set that have had no heart attack. There's 55 people with grade 1, 36 with grade 2, etc. So you can use this, you know, we could do this on any of the columns. If we wanted to take the ages and value counts all of those. So this first part is just the age column. Second part is saying tally them all up in a big table. They haven't ordered them for us. You can capture that and do it yourself if you'd want, but there's 19 people age 58, 17 age 57, etc. So this is useful as well to kind of take a first look at your data set. There's some couple unlucky people who've had heart attacks in their 30s. Okay, so one of the most important things before you get too crazy when you've received some data and you want to start playing with it is to really make sure that you don't have missing data, or maybe you have characters in a column where you're supposed to have this will happen, right? Your instrument doesn't work, and so you're missing a piece of data, and instead of dealing with it, somebody just writes missing or they write NA. This is important for us to check for when we get started. So there's a few helpful functions we can use, which is null, and basically that's going to check for every column of attributes. If you remember, attributes looks like this. It's got each one of our data points for each individual. It's going to, any of those are have a missing value. As we'll find out a little bit later, though, it's only searching for specific missing values. So for every column, it's going to check that, and then I'm asking it to add them all together. So this will tell us how many missing values we have in each column. So at first pass, it looks like the set is fine. There's at least there's some entry in every location in the data frame. What we can also do, what I really like to do when you get one of these, is a function called describe. What this does is for every column, it you have. So we see there's 303 entries in every column, and it gives you some of the useful statistics. What's the mean? What's the standard deviation? And all of your quartiles. And you can use this sometimes to kind of spot check and see are really different from other ones. So we can see here this is probably blood pressure. It ranges from 94 to 200. We've got other things like sex that basically only take the value 0 and 1. So you can kind of get a thing of what your data looks like before we start to build any models from it. So as I said, you know, maybe we got lucky here and don't have any missing values, but if we do, then we need to come up with a strategy to replace them. Okay, so we're section. This is still not machine learning. We're entering what we'd call kind of unsupervised clustering territory. But even before we get there, it's useful for us to take a look at how's our data distributed. Is it normal? Is everything on the same scale? And we humans operate very well visually, so we can take advantage of this. Some really helpful Python packages. So I've given Seaborn this nickname SNS, which just saves us some typing. It's going to take a second. And also matplotlib. This is just going to make our plots a little bit prettier when we do it. So let me show you the first plot, which is a box plot. So Seaborn has this really simple syntax. So seaborn.boxplot, and then we just have to pass it the data that we're using. So in this case, it's attributes, and straight away it should, this as well, plot.show. It should fire up a nice little box plot for us. So as you can see here, let me make it a little bit bigger. How to do this. Yeah, okay, so I think we can say, so I'm just going to tell it to make a slightly bigger figure. Let's do 10 by 8. X is that. Nope. Size, oops, equals. A bit of a bigger plot. So you can see we've got our columns are across the bottom, and this, if you're not used to a box plot, the bar in the middle is the median, and these are the 25% and 75%, and then these whiskers extend out to include some of the points, and then they put dots that are outliers. So we're not going to do much with outliers today because it sort of depends what you're interested in. If you're interested in building a model based on general cases, then you maybe want to trim out your outliers, but sometimes it's useful to actually look at outlier points to see if there's something informative with them. So the next thing that we'd like to do, we've noticed earlier that some of these things are on completely different scales than others, so we really can't tell what is around some of these other so small. This is a problem for us visualizing it, and also build machine learning models. They perform a lot better when all of our attributes are on the same scale. So we're going to pull in our last helpful package, which is called scikit-learn here, and they have a function called an object called a standard scalar that allows us to basically take each of these and transform them to have mean of 0 and standard deviation of 1. And I'll show you how that works. It's just a couple lines of code, and it should make it a lot easier for us to visualize. So scikit-learn is learning library that I discussed earlier. They have a submodule in there called preprocessing, and you should check out their website because it's got very detailed documentation. This works. You'll get used to this if you start using scikit-learn a lot, but first we initialize this scalar object. It doesn't do anything, it just runs fine, and then we can say I want to make a new data frame called attributes scaled. It's a transformation of the original one. So the way to dissect this, the reason it's called fit transform is because it's taking this original data frame, it's using the data to fit a scalar, and then it's going to transform the original data with that scalar and spit it back out as scaled. So I was hinting at this earlier, but this has failed for some reason, and we're going to learn why in a second. So errors can be very cryptic, but if you see at the bottom here, we get this value error, string to float, question mark. Thing is, the scalar tried to take all of our data and transform it a distribution that has mean of 0 and standard deviation of 1, but it encountered a question somewhere in the data. So what's happened is whoever's given us this data set, our colleague or the doctors or whatever, have filled in some missing data in a somewhat non-standard way by putting a question mark in there. So the original test that we did running pd.isNull didn't work for us because it doesn't know to look for question marks, it just knows to look for. So now that we know what it is, we can use a function called replace. So we can, you can replace anything, whatever you want, with whatever you want. In this case, we want to replace the question mark that they've put in with something that's a little bit more standard. This uses the NumPy package, and it's called a stands for not a number. So we're basically saying take these question marks and replace them with something that our software will understand, which is this not a number object. So now I should save it as that. If we function that we ran earlier asking how many nulls are there and then adding them together, we call them and add up all of these NP NaNs, we see that we get a different story. So actually the last two columns, this one has 4 missing values and this one has 2. So it didn't flag earlier because we weren't looking for the question marks. So sometimes this happens, you know, we encounter a weird error like this and I have to go back and check how we got there. So now we can make a decision about what we do with these rows. You may want to replace that data with the median of you may choose to discard it. You might replace it with the mean. You have all sorts of different options. I'll show you how to just get rid of it because there are so few. But in general, if you have a lot of missing data, you use the median or mean to fill it in, so you don't lose data. So we have this function called dropna. Before I run it, just look at the shape of the original one. So if you remember, it had 13 columns and 303 rows. If we were to run dropna, we would have 297 rows. So it's basically 6 rows, 4 of which have that one missing. Go ahead and run that by just saying attributes equals that, drop off this part. So let's try to run this again and see if we can avoid that error. Attribute scaled, great. So we can take a look at this data frame here, attribute scaled, and see what it looks like. Oops. On this fit transform, it actually do a NumPy ND array, not to a data frame. So we actually have to convert it back to a data frame. I've wrapped this up into a data frame. And we've also got to rename its columns. So if we look at this one here, anymore, so we can actually just replace the columns with the same columns that we had before because those haven't been transformed in any way. So let's take a look at our new data frame. As you can see, same columns, but to the eye, this information is not so useful anymore. So this is basically a reflection of how far the person's age is below mean, how many standard deviations below or above the mean. So this is much more helpful for the computer. And it also allows us to say a 1 standard deviation increase in someone's age is equivalent to standard deviation increase in cholesterol. So it puts us sort of on the same scale. Instead of saying 2 years of age is equal to an additional 4 points of cholesterol. So let's take a look at this box plot now, because this is kind of what we did this for in the first place, so we can see how our data is distributed. We should be able to run the same thing that I did before again to make it a little bit bigger. And make it 10 by 8. Show. So we plotted 2 of them. Okay, so there we go. It's now a lot more useful because we can see how everything's distributed. Some of them look a little bit funny, like sex, because they're just 0 and 1, so it looks like this big rectangle. Same with thal, whichever one that is, but the rest you can see are that have crazy amounts of outliers. We have a few here and a few here, but sometimes you'll get something is incredibly skewed in one direction. One drawback of the box plot is you might be obscuring a lot of information in these whiskers. There are other types of plots you can look at, like violin plots, for instance, that show the contours of the data a little bit better. Okay, so before we've scaled our data now, before we can start thinking about building a model, it's also really useful to understand how much redundancy there is in our data. So as you continue to add more attributes, they'll individually become less and less useful. It's because things correlate with one another. So your cholesterol and your blood pressure are probably going to correlate very highly. And so including both of those as information, you're not going to get as much information out of those two as things that are completely independent. And we can, once again, sort of visualize this in a few different ways. The first one, just an example, we'll make LM plot. LM stands for linear model. We're not going to plot a line, although we can. It follows a very similar as the box plot we did before. So we tell it what the data that we want to use is. So this is attribute scaled, and then we tell it what should we put on the x-axis. Let's look at cholesterol versus what we want on the y-axis. And I'm going to tell it to put a regression line, although we can take that off in a second and see what it looks like. Just like with the box plot, we use plot show and see what it looks like. Very cool. Okay, so cholesterol is on the x-axis, blood pressure on the y-axis. You can see there's, maybe some correlation there. If we put true, then it'll draw a line for us and tell us what it thinks the correlation is between these points. So this is very useful at looking at single set. We can also all at once. This is a little bonus. I didn't include it in the slides, but it's a very cool function. So it's called a pair plot. It's going to take us a second. Oh, sorry, and let's see if that runs. Oops, I need to plot show. So what this is doing, the reason it's taking so long is because it's generating one of these scatter plots for every attribute against every other attribute. So it will do age versus sex, age versus CP, age versus resting blood pressure, age versus cholesterol. It's informative, but sometimes if you have too many attributes, then can't see what's going on. And that's when we'll use a heat map, which I'll show you in a second as soon as this finishes. There we go. Okay, so there's a lot of information coming at us here. So on the diagonal here, age versus age, it's showing us a histogram that's a distribution of the ages. Same here, this is a distribution of the sexes of CP, and then on the off diagonals you can see each of them versus one another. So I know it's very difficult to see because it's so tiny. First column is age, and the fourth one is blood pressure. So this cloud here shows age versus blood pressure. One thing that I like to do sometimes is out. Let's do all of the rows and the first 5 columns. It'll take as long this time, and we should get easier to see. So this is just the first 5 columns against one another. So age versus sex. As you can see, there's really not a huge amount of correlation there. Age versus CP, this is age versus blood pressure, and that's age versus cholesterol. So this gives us a little bit of an idea of how much underlying variation we have in each of our, also which ones, if you have to make simplifying assumptions to combine features together or remove them, then correlation is a good way to start by removing features which correlate very highly. One more way to take a look at this is making this correlation matrix. I'm just going to do steal it from up here again. Make it so it's a little bit bigger. So what this thing is taking of columns, so age and sex, age and CP, age and blood pressure, and getting a correlation between them. So this will be some value between 0 and 1, 1 being perfectly correlated, 0 being uncorrelated. We can feed this information to, again, same setup, sns.heatmap. You tell it the data that we want to use, core here, and I'm colorblind, so I'm going to give it a friendly colorblind palette, and keep forgetting the plot show. There we go. We get this really nice looking heat map. We got 2 of them actually. The color in the square represents the degree of correlation between those 2 attributes. So we have this dark blue all along the diagonal. It's because obviously age correlates perfectly with age. But if you look on the off diagonals, you can see, for instance, there's a big block down here. All of these 5 things tend to correlate very highly with one another. So it may be that later down the line we make a simplifying assumption to choose representative. This would happen if this might happen if you're using something like a lasso regression, which is like a linear regression, but you remove some of the features. You only focus on a handful of them to simplify the model. You can also see this when you do principal component analysis, which is another tool that you learn pretty early in the feature engineering toolbook. You'll see that these things all correlate with one another, and you can collapse them down. This is a taster session here for this webinar, so we're not going to get into any of those, but you can see here, everything correlates with everything to some degree. And we can use these to make simplifying assumptions in our model. So I'll just show you the Seaborn idea of all the different things you can do. They've got tutorials. Here's a more complicated heat map with a hierarchical clustering on the top. Encourage you to take a look around and get some inspiration. The second thing that I mentioned was there's quite a lot on the website. If we go to /content, then cool stuff. So you can do spatial data, make a spam filter, learn how to make a recommender system. So if something piques your interest here, if you like genetics, then you can check that one out. Check it out. And then also, you can find this on the website, but if you want to sign up to the bootcamp or check it out, then link on the website, and you can see here there's another one that starts in February. So these will start with basic feature engineering and then move pretty quickly to more complicated machine learning models. Just to finish up here, I'll want to recap. I think most important thing to take away from feature engineering is that limited by the quality of the data and the quantity that you have. So assuming that you receive a fixed quantity of data from whoever you're working with, the study that you're involved in, you can really squeeze out a lot of interesting by focusing on quality control. It's not the sexiest part of the job, but it is by far the most important. And you'll find that you spend probably a little bit more than half of your time doing these things, because if you don't, you'll be consistently frustrated by, you'll run a model, work, or maybe it will work, but for all the wrong reasons, then you'll have to go back and start over. So the tools presented here are, but there's a lot more that you can still learn. So I'll just, for what we covered. Loading data from an external file. The main takeaway from Pandas is it's a very user-friendly interface for working with tabular data. If you're used to working in Excel, then it's a very simple way to get started. And it's the most commonly used tool for data scientists. So it's something that you'll really get a lot of use out of if you spend the time learning the basics. And then we spent a little bit of time on the plotting package Seaborn. There are others. Matplotlib is another very common one that Seaborn is actually kind of built on top of to add functionalities. But you'll play around with these and find your favorites, and you'll be able to make some really and then we just got started on scikit-learn, but if you end up coming to any more of the conferences or courses, then you'll learn a lot more of those tools, how to build classifiers, how to do principal component analysis, reduce the dimension of your data, those sorts of things. If you have any questions, please feel free to leave comments on the YouTube channel, send us a message, and if links here that I put in the beginning. If anything is of interest to you, or if you have any questions about how these things work, then you can feel free to get in touch with us. Thanks a lot for listening, and the rest of your day, wherever you are. Maybe it's nighttime in England, but maybe some of you are other parts of the world and just getting the day started. So thanks.